Tim Essington, the co-chair for this session, is a faculty member here at SAFS and has worked a lot. I think he's going to talk. He's been on a number of different committees. I can't keep reading fast enough to read as fast as he's writing papers, and so I'm constantly being surprised by work that I haven't seen. And this will be no exception. I think it'll be new to some of you. And Tim is going to talk to us about barriers between principle and practice. Thank you.
Thanks, Dave. Hope this is working okay. So I thought I was going to start with some crack about thanking the session chairs for inviting me, but that seemed a little too easy, so I won't. Thanks everyone for the presentation this session. I've learned a lot. It's been great to hear all the different perspectives. And selfishly, it's actually set up a lot of the stuff that I wanted to say really nicely. So it's going to be hopefully some nice overlap. So I'm going to want to get over this idea that there's a lot of scientific principles for ecosystem-based management. We see there are some areas where we could perhaps do better, and I want to sort of take my take on how do we deal with the issue of the complexity that's involved in natural systems and translate that into sort of meaningful, simple, tangible advice, sort of getting to Stephanie's issue of making it clear what it is we're trying to do and why we're trying to do it. So I'm going to start off with a premise that I think most of us will agree with, is this idea that ecosystems are complex. You know, there's a jumbled mess of connections. Oops. Either this died or I'm pointing at myself. Here we go. So we know they're complex, and we know they're changing, and we know that we'll never perfectly be able to map all of those different connections within systems. But maybe a question to follow, does that mean that an ecosystem-based management approach also needs to be complex? And gosh, I can't remember the year, but there was a Moat Fishery Symposium that was all on the application of ecosystem-based fisheries management. Of course, Ray was there, being a rabble-rouser. And he said, well, if we did single species management well, would we have to do any sort of ecosystem-based fisheries management? And we thought, I don't know. But I thought it's actually worthwhile to actually turn the question around, and what if we sort of approach the question in a totally different way? As Stephanie said, ecosystem-based management is a way of thinking, and what if we just thought about the question differently? Would it actually lead to sort of a simpler way of managing systems? And would we achieve sort of these broader ecological goals or ecosystem goals while also meeting all the other goals that we have in fisheries management? So that was sort of a thought experiment that sort of underlies the outline of sort of what I'm going to talk about in this presentation. I'm not going to answer that, but that was sort of what I was thinking about. Okay, so I also started thinking about, well, what sort of currently seems to be sort of in scope in terms of what seems to happen in fisheries management with respect to ecosystem principles. Bycatch is certainly, it's in scope. We talk about a lot, achieving optimal yield, ending overfishing, that's certainly sort of within the scope. Managing stocks as a unit, that's sort of in scope. Using best available scientific information so that we're dealing with, this guy really is dying, I'll just point. Habitat, dealing with environmental force and stuff that Ann Holloway talked about earlier, making sort of predictions. That's sort of all sort of within the purview of what we're currently doing. I think we're doing a decent job on a lot of those components. The parts where I think that we're sort of mostly out of scope and areas where I think there's perhaps room for improvement or progress is dealing with two really tricky issues, and Selena talked about at least one of these. First is the idea of trade-offs. It's the idea that you, once you take biomass out of an ecosystem, you're taking that out, and that might have been used by something else that we also really value. And that introduces trade-offs. And the second is the really sticky issue of cumulative impacts. How do you look across different use sectors? So that includes impacts on land, shipping, oil exploration, climate change, superimposing fishing on top of that. How do you then come to wrestle with those? And those are really thorny, difficult problems. In fact, they're so thorny and difficult, I'm not going to talk about this at all, and talk about mostly this side, which I have given a little bit more thought to. And from here on in, I'm going to just totally go all in on forage fish. Thanks, Selena, for introducing it. I'm going to talk about forage fish for a couple of reasons. First, I know a little bit about them, so I feel I can fill 30 minutes relatively easily talking about forage fish. The second, though, I think it's an interesting case or example or area of interest that's obviously relevant for the Magnuson-Stevens Authorization Act, given the Senate language. But it reveals some of the issues of trade-offs and it reveals sort of what my vision is of how I think we can go from complexity of actual systems into fairly simple guidance that, on average, are going to work pretty well. So that's kind of the overall theme of what I hope to get across in this presentation. So there's sort of two views about ecosystems and food webs, and in particular the roles of forage fish within them. And you just saw the slide about 15 minutes ago that Selena presented. This has forage fish right smack in the middle of them. And under this view, forage fish are a key linkage in food webs. What they do is they gobble up all of these little tiny particles and turn those into these delicious, fatty little packets that aggregate up together that are easy pickings for a lot of fish species that we like to go fishing for a lot of marine mammals that people like to know that they exist or like to go looking at, and a lot of seabirds that people also are fond of. So that's sort of one view of how ecosystems are structured. The opposing views are that food webs are a complete jumbled mess. This is sort of similar to the horrendogram that Selena showed a minute ago, where there's a gajillion pathways to get from any box to another. You never know, how you should undo all of this, in which case it's completely intractable and you can't make any progress going forward. So I'm going to sort of talk about three sort of vignettes looking at forage fish to try to deal with this complexity in terms of giving just some straightforward management guidance that sort of are very simple guidance that deals with a very complex system. The first, I'm going to talk about rules of thumb that you can use to minimize the trade-offs between forage fish fisheries and other ecological benefits that we derive from them. Talking about screening tools to do the type of triage that Tony Smith talked about earlier today to identify what species do we really need to pay particular attention to. And then lastly, avoiding really, really bad outcomes, the uh-oh moments when we really screw up, and when those uh-oh moments happen, they percolate all the way through the food web. So those are going to be the three big things I want to talk about today. So this whole issue of trade-offs in terms of forage fish and just looking at trade-offs just within fisheries really deal with this sort of basic question. I need to acknowledge Laura Cohen, who put this really great graphic together. What we really want to know is if we incrementally take out one more, say, sardine or herring or your favorite small silvery fish, what is the loss of yield you get from a predator that might have eaten that and then we might have eventually caught? Okay? That's sort of the big question, and it's a hard one to know with a high degree of precision. So one way that we can think about these trade-offs is if we can sort of integrate over all the different pathways that energy moves through food webs and species interact with each other. What we're looking at is at a given point in time, we know there's a certain amount of yield we're getting presently of forage fish, and there's a given amount of yield we're getting on a predator. And what we want to know, if we were to take just a little bit more forage fish, what would we lose in terms of the catch of a predator? So maybe it's totally flat. There's no trade-off at all. If you catch a little bit more, it really doesn't have a very big effect. We might see a striking negative relationship. That would be a very strong trade-off. So you catch a little bit more forage fish, and the loss you get is the yield of a strong loss of yield of predators. Or because of the complicated nature of pathways through food webs, you could actually get an increase because energy is sort of moving around in sort of unexpected ways. So what we wanted to do was sort of develop sort of quick, robust ways to try to get some sense. I can't describe the exact outcome, but it would be really great if I at least knew the slope of this relationship at some point in time. That would be really helpful guidelines. And it would be even better if I could predict what dictates the strength of that slope. And if I can, then I can start developing guidelines of how do I stay away from the zone where I get these really, really strong negative relationships. Because that's where I get into a nasty realm of having really strong trade-offs and conflicts among different users. Oh, there's my first Mac to PC goof. That's not bad, though. Been working with Steve Munch, who's down at the Santa Cruz NOAA lab, to develop just a simple way of trying to get this that doesn't involve doing a lot of complex food web simulations, where we take data on food webs, so how much do different things eat, what do they eat, how much are there out there. We put that into this very generalized model. The nice thing about it's a very easy model. You can have very transparent assumptions about what is the nature of species interactions. Then math happens. And then that produces these estimates of what that slope is that tell us what is the incremental loss of yield of a predator that happens from changing your forage fish yield by just a little bit. And the nice thing about this, because it doesn't involve a gajillion simulations, I can look over a bunch of different ecosystems around the world and basically pillaging other people's food web models. And I can look, each of those models might have as many as 5 or 6 different forage species, and each of those might have 5 or 6, 7 predators on them. So I can start looking at attributes of both the food web structure and attributes of the individual predator-prey linkage and say, well, what's a good predictor of the strength of that trade-off? And this is kind of the bottom line of all of that process in math, is there were 2 things that really seemed to dictate what was the strength of the trade-off. The first is sort of intuitive. As the intensity of the linkage between a particular predator and a prey got stronger and stronger, the trade-off that you get from plucking out that sardine in terms of predator fish yield strengthens. And that made total sense. The thing that I didn't expect is that that relationship itself depends on how heavily you're fishing the forage fish in the first place. So if you're fishing the forage fish relatively lightly, it doesn't really matter. Even if you have a relatively strong predator-prey linkage, you never really get in a zone with a really, really strong trade-off. And one little just sort of orientation point I put on here, I put a line of a trade-off slope of minus 10%. And the only reason I did that is sort of on average, the price per pound and sort of landed value of forage fish tends to be about 10% of what it is for a piscivore that might have eaten that. So whenever you sort of get below this line, that's where the forage fish is probably more valuable in the ocean than being caught. So this orange line sort of shows the line you would get with Rick Bethott's sort of happy place when you're fishing sort of at a 75 or maybe slightly less than 75% of what the normal exploitation rate would be on a stock. And that actually gets you in a pretty happy place in terms of these trade-off issues as well. It's only when you're fishing really, really strong at full MSY do you get really strong trade-offs for lots of different predators. So this was sort of a cartoon. The reality, though, there's still a lot of variation around those slopes. That particular relationship explains something like 35% of all the trade-offs. So we're never going to be able to nail all of those. And you do still get a lot of these interesting positive trade-offs, which actually aren't trade-offs at all. It means if you fish forage fish, you actually get a little bit more of some particular predators. And that has to do with the complicated jumbledness of all of the ecological interactions. But that said, you can do a lot without knowing every single pathway of how energy moves up into the things we catch. You know, simply having slightly lower target rates avoids the very worst trade-offs, even for the strongest predator-prey linkage. Doing that would also prevent against the accidental overfishing that we heard about. That happens when you think you're setting the right quotas, but it turns out in retrospect the stock biomass is not as abundant as you thought it was. And this is particularly an issue for forage fish, because you can catch forage fish at really high rates even when they're not very abundant, because they have this nice convenient habit of schooling together. And as long as you can find that school and put the net in, you're going to catch a lot of fish sort of regardless of what the overall population abundance is. And then the loss of yield, as we saw, if we're sort of dealing in the pretty good yield realm, it turns out the pretty good yield actually avoids a lot of these trade-offs between forage fish and other things. And just rough calculations, you could lose maybe 25% compared to FMSY and avoid all these sticky issues of, whose energy in the food web is it? Does it belong to the tunas? Does it belong to the forage fish? And I'm going to show you later on in the talk, if you have a sort of a fancier set of rules that adjust the exploitation intensity based on how productive the stock is, you actually get almost no losses at all. So this is just one example of translating all the complexity into food webs into some simple rules of thumb that on average are going to get you out of the zone where you really don't want to be. Okay, the next thing I want to talk about is this idea that some forage fish species are more key than others, and how can we better flag those? How can we better identify those? So this is building off of work that actually Tony published a couple of years ago. It's a really great paper that compiled a bunch of models, different types of models from a bunch of different systems, where they could do different simulations to look at the effect of fishing forage species. So these are the small pelagic fish, also some of the mesopelagic fish, also krill and things like that, on predators But one of the things that really stuck out with me was this recognition that some forage fish are more important than others. In other words, if you diminish their abundance by fishing, you had much stronger effects throughout the ecosystem than other forage species. And they made some efforts to try to identify some metrics that might be used to sort of flag, well, these are the stocks. If you diminish those, there are a lot of these percolating effects within the food web. It turns out, though, those were not hugely precise. And because I work with Australian, we came up with a cool new acronym called SURF, which is a new metric that we've proposed that can better flag what species are most likely to have really profound implications of depletion. So Eva Plagani came up with this. The name of our paper, it's still in review, is When the Surf is Up, the Fish is Key. So we came up with a classic, you come up with the name and you figure out what it means afterwards. So we started with surf because it sounded cool. Then we figured out that means supportive role to fisheries, which was a simple index that could be used using data that are available that might be able to robustly identify those species that we think if we fish those hard will have a lot of effects within the ecosystems. It basically scales food web linkages by the strength of those interactions, so the diet fraction, so how much of a particular predator's diet is composed of that particular species. And importantly, it's not a linear relationship, so it weights high diet fractions very strongly. So a very few number of high linkages get scored much higher than lots of weak linkages. So we took these same simulations that Tony and his colleagues had used in his simulation, and we saw how well our surf index could discriminate between stocks that had a really high impact on the food web versus those that did not. So the connectance is simply how many different connections in a food web include that particular species, and this was the indicator that Tony's group proposed. And what they've done here is put every single dot is a forage species, and the rank of impact goes up where 1 is a pretty minor impact, nobody really cares if you deplete it. 2 is a couple species get depleted by moderate amounts, but no species really are devastated. And a rank of 3 means you either have a bunch of species that are all having a moderate impact, or at least one species is really upset about the whole situation. So you really want to avoid these rank 3 effects. And if you use connectance, so what fraction of all the connections go through a particular species, and you sort of look at 0.4, it seems to do a reasonable job of flagging some of these rank 3s. It misses this guy right there. But one problem with connectance is it's also lumping all of these guys as saying these are really key, when in fact, like this one in particular, really that was not a particularly important species. Surf, on the other hand, does a marvelous job of distinguishing the rank 1 and rank 2 species. So these are the ones, if you deplete them, either no one cares or maybe just someone cares a little bit, from those where there's a lot of widespread impacts. So what we're proposing is, many places around the world we have these types of diet data. We don't need to build an entire food web model. Just need to know what the predators are and how much they eat. And you can calculate this surf, just use a spreadsheet. You could probably do it with pencil and paper if you really wanted to. And you can quickly figure out, are you up here? Are you one of these rank 3 really key species? Or are you one of these where maybe you don't need to put any extra restrictions on fishing, because that species isn't likely to have a lot of far-reaching ecological effects. Okay, so sort of gone through 2 examples of how we can translate the complexity of actual systems into simplicity. First with these rules of thumbs to minimize trade-offs, and then this quick rapid screening tools that allow you to quickly sort of do the triage to figure out whether or not you really need to have perhaps a lower harvest rate. The last thing I want to talk about is the idea of putting in some policies that would avoid these really bad or tragic outcomes. So Philippe Curry and Ian Boyd were part of the Lenfish Forage Fish Task Force, and one of the first things they did on sort of a side project is convene a bunch of experts that had data on seabird reproductive success from around the world. And they were really interested in sort of parameterizing, well, what's the relationship between the availability of forage fish for these seabirds and some measure of their reproductive output. And the key take-home message from their paper was this graph right here, which basically showed that if you have a lot of forage fish present, I can just point, I'm right next to it. Basically, if you're above average, right here, most fish, or most seabirds really don't care if there are fluctuations left or right, okay? But they really start care once you drop below here. So when resources get scarce, that's when you really start to see the effects. And we've all seen, I think we've all had parts in our lives where resources were scarce, and a little bit extra resource really meant a lot. In fact, we've seen it a lot the last couple days. SAS graduate students are wonderful, and they're woefully paid. So as a result, additional box lunch that's available is a really big deal to them, right? It's a very happy day when they get a box lunch. So we had box lunches, but the dean of the college, Lisa Gromlich, didn't go running out of her office to get her free box lunch because she's up here. She's doing fine. She doesn't need the box lunch.
This is being recorded.
I know. Yeah. Well, I think it's good that our dean is paid slightly more than a graduate student. I think that seems appropriate to me. So what we want to do is stay out of the graduate student zone and get to the point where every single unit of box lunch really matters. In fact, they sort of flock like seabirds, when they came out. They go running away with the box lunches to their offices. So that's sort of what we want to avoid. But how do we deal with that when we know that forage fish populations are inherently highly variable and highly fluctuating? So these are data from sort of a cherry-picked set of stocks. This should show the different flavors of environmental variability. And there's no scale on here, so you don't get too distracted. But the bottom line is the dotted line for each of these shows the long-term average population. And these stocks don't spend a whole lot of time near their average population biomass. In fact, they often go up about 5 times their average biomass and then come crashing down to really low levels, and they come back up and they come crashing down. Okay? So these animals are sort of going through periods of being the dean of the college, and then they're graduate students, and then they're deans again, and then they're graduate students. So that's sort of what the seabirds are sort of experiencing. And what we want to do is really have protections that happen not so much up here, right, because everything's fine. They got plenty of food. It's putting in protections when the forage fish stocks get really low, because that's when every little extra box lunch, that's when every little extra sardine really, really matters at that point. So you might think of, well, what are some reasonable rules of thumb to use to make sure that happens? Well, during these productivity peaks, business as usual. Go fishing, have fun, do whatever you want to do. During intermediate periods, add a little bit of caution because there is this implementation area. You don't always get the stock assessment just right. And when you screw it up, you affect a lot more than just the target stock. And then obviously when the harvest rates or when the productivity really gets low, it's a good idea to probably stop fishing because that's when the benefits to the ecosystem are really get magnified. So that seems like a reasonable rule of thumb. So I've been looking at some of the data around the world in forage fish stocks to see whether or not, in fact, we follow this particular bit of guidance. Sadly, no, we've done the exact opposite in almost every case where these forage fish stocks have collapsed. That's been accompanied by periods of very heavy exploitation rate. So what this shows is standardized biomass, so standardized relative to the mean. So 1 is the mean. And these are all stocks that collapse to about 1/4 of their average biomass. And the color of the line at any given point is proportional to what its exploitation rate in that year was. Okay? And these are going all the way up to 0.8. So some of these things are catching 80% of the biomass in a given year. Big thing here, there's a lot of red and orange and yellow, very high exploitation rates. And then the uh-oh happens. And then we can fix that, and then exploitation rates get lowered. If you sort of plot the sort of distribution of exploitation rates through time as a function of years since collapse, you see this ratchet up of exploitation rates. So we're doing the exact opposite of what you'd want to do. Exploitation rates are getting higher and higher as the stocks are crashing, and then there's a lag, and finally you catch it and you come back down. I should note these average exploitation rates are about twice what they are on average across all the other stocks. So, and this is all just due to what Rick Mathot talked about yesterday. Primarily, we got the stock size wrong, and there's lags in our ability to detect that. So it's not as though people are being devious about this. It's just honest mistake. It turns out you can do some simulations to say, well, what does that mean about when these stocks are fluctuating? Where is the bottom of that trough? right? Because we want to make sure that we make the bottom of the trough as high as possible, because that's where things are really, really sensitive. This is the distribution of the minimum observed biomass expressed as the biomass relative to the mean. There's this big peak here, which is associated with less than 5%, or between 0 and 5% of the average biomass. And you can even ask, well, would you expect to see this particular distribution of minimum stock biomasses if there was no fishing going on? So what I've done here, the blue line is translating this histogram into a cumulative probability distribution. So this tells you what fraction of the observed stocks had a cumulative biomass less than or equal to that. That gives you the blue line. The orange line is where stocks would be if it wasn't for fishing. And what we see is we see a lot more of these than you would expect just based on random, which is not too surprising when you're talking about 80% fishing mortality rates when stocks are coming down. So I think I'm calling this the trophic boot print of fisheries, right? So they're coming down, they're going down anyways, and we just kind of stomp on them by mistake. That pushes them down to these really, really low levels. And we know that's where all the really bad ecological outcomes really happen. So just as a thought experiment, I said, well, what if there was perfect management in all these cases, perfect stock guidance, and it followed a really simple harvest control rule that you fish according to a normal until you reach half your average biomass. What would have been the minimum biomass of those populations, and what would have been the loss yield? Well, it turns out if you do that, the minimum biomass doubles for these stocks that all collapsed. So if they collapsed at 25%, they would bump all the way up to 0.5. If they collapsed at 10%, they would go all the way up to 20%. The loss yield, there wasn't any. In fact, there was this marginal increase in yield you get because the stocks rebound so much faster. So just being able to have some warning signs that these stocks are coming down so you can implement one of these things would lead to really improved ecological conditions with actually a small benefit to fisheries. So just to sum up sort of my take on this barrier between principle and practice, I think if we were successful in reaching all of the goals of the ecosystem approaches to fisheries management, we would generally get all of the other goals of management would probably be encompassed within there. There are many cases where adopting ecological goals and objectives have very little effective yield, and those are the low-hanging fruits. There's no reason for us not to go for those. But I think the key is this translation is going from the complexity of the real system to a simple operational set of decisions and guidelines that make sense to everybody. And I'm going to end with an announcement. The ink just dried on this agreement this week is a new LENFEST task force that's going to start this summer. It's the Fishery Ecosystem Planning Task Force. And what our charge is to provide a blueprint for fisheries management councils in the United States to develop and implement ecosystem-based fisheries management. Phil Levin is the co-chair. He's very excited about it, as you can tell, and there's going to be some formal announcement. It turns out about 1/4 of the task force is in this room and talked in this session. But one thing that's really going to be innovative about this task force is we're going to work very closely with an advisory body that consists of council members and NOAA staffers and also members of other agencies from international bodies to make sure we don't go off in academic la-la land, but we're really well grounded, that we're really providing really useful tools that basically guide this process of going from what the science think needs to happen and what the policymakers can actually do. Thank you.